In this second section, we're going to discuss indefinite integrals and the substitution method. All right, as you will recall, in indefinite integral is an integral without limits of integration, right? It looks like this, the integral or the indefinite integral of f of x dx. Remember, that is just an antiderivative capital F of x plus c, where capital F of x is the antiderivative and c is a constant of integration, some real number, okay? And so, of course, as a review, we're going to look at part A here where we find, not find, but find the indefinite integral. All right, so finding the indefinite integral is the same thing as finding the antiderivative. So we have 2x plus 1. Remember, this follows our power rule. And so we can find the antiderivative by raising that exponent by, so the constant stays out front, the coefficient. But if I increase the exponent by 2, this is understood to be an exponent of 1. 1 plus 1 is 2. And I divide by that same exponent. That'll give me the antiderivative of 2x. And the antiderivative of a constant equals x. Okay? And then I have my plus c. And so this equals x squared plus x plus c, right? Remember, we can check ourselves by finding the derivative. And so the derivative of 2x or x squared with respect to x is 2x. The derivative of x with respect to x is 1, which is what we started with from the beginning, right? Remember, when we see this and there's no limits of integration, we just find our general antiderivative. If there were limits of integration, let's say that there was an a and a b there, then we would go to here and plug in b into that and then subtract what we get when we plug in a. That's what we learned in the last section, but we're going back to this indefinite case. And so now we're going to look at other examples that may be a little bit more complicated. And actually, I want to get rid of some of this space here so I can provide more space. Unfortunately, you don't have that opportunity on your paper. But I am going to do it on mine. All right, so we're going to do the integral of, my integrand here is 2x times e to the x squared dx, right? And so when I see this, I got to find the antiderivative, okay? Well, this is hard because I don't know what the antiderivative, what function whose derivative will give me this. Some of you may know, but it's kind of hard to tell. It's really kind of hard to see. And one of the things that make this hard is because I have this 2x, which is one function, multiplied by this function here, which is e to the x squared, okay? And I want you to notice something. There's something about both of these parts here that we want to figure out. For instance, one of the things that I know is that e to the x squared is a composite function. It's composed of two separate functions, right? For instance, let's say it's the inside and the outside part, right? My outside function would be e to the x. And if that's my outside, then my inside function would be x squared, right? And so e to the x squared is the same thing as f of g of x, right? Where this is my inside and this is my outside function, right? Another thing that you should notice here is that 2x is the derivative of the inside function, g of x, right? So if I find g prime of x, that equals 2x. And so what we have sitting here is basically this integral that we're given can be written as f of g of x times g prime of x dx. Because that 2x, I know it's written set first in there, but that 2x represents the g prime of x, and that e to the x squared, that's that f of g of x, okay? And so what we're going to do is we're going to find out how we can find antiderivatives when we see the derivative, and actually what we're going to find out is that we're going to see the derivative of this function sitting here as well, but we'll formalize that in our next example. Now, this actually only happens for f of g of x in this example, But I have a function, a composite function with its derivative sitting there, and I want to find the antiderivative. And I'm going to walk you through the steps that we use to do that, right? So anytime we have something like this, we use a method called U-Substitution. I think I spelled that right, but there it is, right? And so one of the first things we're going to do, I'm going to write this in like 5 steps. So the first thing we're going to do is we're going to let u equal that function g of x, that function whose derivative, that inside function, right? So in our case, u equals x squared. Then we're going to take the derivative with respect to x on both sides of this equation. So we're going to go here to where u equals that value, the inside function, and we're going to take the derivative with respect to x. And so the derivative of u with respect to x is du dx, and the derivative of x squared with respect to x is 2x. Now, what we do in order to do what we call a U-substitution is what I'm going to do, and this is going to seem very weird, but we're going to leave this du on one side by itself. So we're going to leave the du on one side by itself. That means we're going to multiply both sides by dx. Now, I know that seems weird, but this is what's going to happen. And this is going to allow us to write everything in terms of u instead of writing it in terms of x. So the dx is canceled on this side. And so I'm going to be left with a du, and that's going to leave me with a 2x dx. All right. Now that I have this, notice this 2x dx is sitting here and sitting here in my integral. Okay. My x squared here is sitting here in my integrand, which is in that composite function. And so what we're going to do next is we're going to rewrite everything in terms of u instead of x. And this is the way we're going to do it, right? So I started out with the integral of 2x e to the x squared dx. Parenthesis is there, right? And I want to write this as an integral. Again, this x squared is going to be replaced by u, and this 2x and that dx is going to be replaced by du. And so my integral is going to become e to the u du, right? This du takes care of that 2x and dx, and this u is taken care of by that x squared, right? And so now that I have everything in terms of x, I'm going to find the antiderivative. So I'm going to do it up here. And so the antiderivative of e to something is e to that something plus c. And then step 5, we're going to rewrite in terms of the original variable. And my original variable in this example was x, right? And so since we went and we let x be the same thing u be the same thing as x squared, and my last step where I rewrite in terms of the original variable is going to be e to the x squared plus c. And this is what that antiderivative or that integral that I started with, which is here, that is what it equals. Remember, you can check yourself. If I do the derivative of e to the x squared, it's going to be e to the something. By the chain rule, I've got to multiply it by the derivative of the inside function, which is 2x. And the derivative of c is 0. So I get 2x e to the x squared, which is what I started with. All right. This method, again, is called the U-substitution or the substitution method. And we formalize it here in theorem 6. Integration by substitution. If u equals g of x is a differentiable function whose range is an interval I and f is continuous on the interval I, then the integral of f of g of x times g prime of x dx is, what is that equal to, you may think? F, capital F, of g of x plus c, okay? Notice we did the antiderivative of that inside function, of the outside function, which is this f of this composite function, e to the x squared, right? And so we did the antiderivative of that, and that gave us this e to the u, which became e to the x squared. And so that is what our theorem 6 is going to say. Sorry about this. Ugh. And so just as a review, our steps in the substitution method is basically we substitute u equals g of x and du equals g prime of x dx into our integrand for our integral to obtain the integral of f of u du. We integrate with respect to u, and then we replace u with its value in terms of x, which was g of x, okay? Let's do multiple examples. This is not an easy concept to grasp. And so a lot of people say the more examples you are exposed to and you do and understand, the better at this you will get. All right, and so let's do this, a couple of examples. Let's look at part A. I have the indefinite integral of 7 times the square root of 7x minus 1. Notice we do have a composition of functions, right? We have an inside function as 7x minus 1 and an outside function as the square root of x. We still have this 7 here. Notice that 7 is the derivative of this inside function, 7x minus 1. So that's a clue that we're going to use U-substitution, all right? And so what we're going to do is we're going to let u equals that inside function, 7x minus 1. Then that means if I do my derivative of u with respect to x, I'm going to get du over dx. Now, I'm going to stop writing du over dx because what we're going to pretty much always do is multiply both sides by dx, right? But I'm going to the right-hand side. The derivative of that with respect to x is 7. And so again, we can multiply both sides by dx so that we can exchange or cancel out the x's here. So I can write this in terms of just u, right? Remember, we want to write our integral just with respect to u. And so we get this thing here. So what I'm going to do is I'm just going to, whenever I do the integral of u, I'm going to write it as du. And whenever I do the integral of this side, I'm going to attach a dx to that. And that way I don't have to worry about multiplying both sides by dx each time. Save you some steps. And so what we're going to do is we're going to replace 7 times dx. Notice this is a 7 times that times dx, right? We're going to replace that with du, and we're going to replace 7x minus 1, which is under that square root, with u. And so my integral that I started with, so this integral is going to equal the indefinite integral of the square root of u and then du, right? That 7 and that dx is du, and that 7x minus 1 is the u. So we simplified this into something that we now can take the antiderivative of using our anti-differentiation rules. That is u to the 1/2 power. Remember, we increased the exponent by 1. 1/2 plus 1 is 3/2. We divide that by the same exponent plus c. And so that just equals 2/3 u to the 3/2 plus c, which we let u equal 7x plus 1, 7x minus 1. And so that'll be 2/3 times 7x minus 1 to the 3/2 plus c. And that is my antiderivative of that function. All right, let's go to part B. This was difficult, so let's work our way through this. One of the things I have here is a mistake. We want to make sure that we have a dx in there, or it doesn't make sense. All right. All right, so what we want to make sure that we always see is a function and its derivative, right? Especially a composite function and its derivative, right? Well, this is a composite function, but it's a triple composite function, right? Because we're squaring the cosine function, but inside the cosine function, we have a 1 over x, right? So it's like an f of g of h of x, right? Where our outermost function is the squaring function. Our next level outer function is our cosine function, and our inner function is 1 over x. All right. So if I look at the innermost function, this is 1 over x. This sort of has the derivative of 1 over x sitting here, right? It has a form of it, right? Because if I think of 1 over x, that's x to the -1 power, right? And if I do the derivative of that, the prime, I bring that -1 out front and I decrease the exponent by 1. Now, in this case, it should have a negative sign out front, but this does not have a negative sign out front. We'll see how we can handle that in this example here. But again, I'm going to let my u be my innermost function, right? So I know I have two inner functions, cosine and 1 over x squared. I'm going to let u be my innermost function, all right? I'm going to find my derivative with respect to x. So it's going to be du equals, that's going to be a negative 1 over x squared dx. Again, I don't have a negative sitting here, right? And so what we can do, anytime when you do the derivative, there's a coefficient on that function that you don't see in the original integrand, then what you can do is multiply or divide both sides by that value, okay? And so what I'm going to do is I'm going to multiply both sides by a negative 1, or you can say divide. It's the same thing, okay? And that's going to give me a negative du equals that 1 over x squared dx. And so now I'm at the point where I'm going to replace this 1 over x squared dx, 1 over x squared, and that dx, that's going to become negative du. And then my u is this 1 over x here, right? So my integral that I'm given is going to be able to be written this way. Now I'm going to write it a little weird, and we're going to straighten it up, all right? So I'm going to have that cosine squared. Instead of 1 over x, it's going to be a u, and it's going to be multiplied by a negative 1 times du, right? Because a negative is multiplied by a negative 1. Now, remember, when we have an integral, we can always bring the coefficient out front of the integral, right? And so I'm going to write this as a negative integral of cosine squared of u du. And now, basically, whenever we have a coefficient on this side of our equation, it can come out front. And so that's kind of a shortcut for you to use in the future. And so now this is very much more simplified compared to what we had at first. And so we go to our try to think of finding the antiderivative of something like this. Well, if you think about our trig functions, all of our antiderivatives are of the cosine, sine, tangent, secant, cosecant, and cotangent. Those are all to the first power, right? There's no exponent on those. So we don't know how to take the antiderivative when there's a power on our trig functions. Unless there's a secant squared, because the antiderivative of secant squared is tangent, right? Because the derivative of tangent is secant squared. But there's not one for sine and cosine squared, all right? Or secant and well, I just said that. Or tangent and cotangent squared. And so what we're going to have to do is we're going to have to think about all of the trigonometry that we know. I know this looks like a 1 here. This should be a 2. I know some of your faces are like, what? And so what we're going to do is we're going to use some trigonometric identities. There's an identity called the double angle formula from trigonometry. These things are going to come up, folks. That says we can write the cosine squared of theta as 1 plus the cosine of 2 theta over 2, all right? And so what I'm going to do is, instead of having a theta here, I have a u. So I'm going to write this as 1 plus the cosine of 2u over 2. And that's still going to be a du, right? Remember, this is a division by 2. Dividing by 2 is the same thing as multiplying by half. Now, this is not what that equals. And so I'm going to bring this 1/2 out front and multiply by this negative 1 that's understood to be there. So I'm going to have a negative 1/2 times the integral of 1 plus the cosine of 2 theta 2u du. And now I can find the antiderivative of 1, and I can find the antiderivative of cosine of 2u using the cosine of k times u. And so this is going to be a negative 1/2. Since there's more than one term, there's a separation with a plus sign. I find the antiderivative, and I'm going to multiply everything by negative 1/2 at the end. Antiderivative of 1 with respect to u is u, because if I take the derivative of u, I'm going to get 1. Antiderivative of cosine of 2u is 1/2 cosine of 2u. And so since we're doing an indefinite integral, I got to remember to put my plus c. I'm going to distribute my negative 1/2. And that's what I get there, right? And so my last step is to write everything in terms of x, right? Remember, u was said to be equal to 1 over x. So everywhere I see a u, I'm going to replace it with 1 over x. So I'm going to get a negative 1/2 times 1 over x minus 1/4 times the cosine of 2 times 1 over x plus c. And so that'll be a negative 1 over 2x minus 1/4. Oh my gosh, I made a mistake. The antiderivative of cosine is sine. So this should be a sine right here. And all of those should be a sine. I'm so sorry. Again, your instructor makes mistakes. Sine. And so that's going to be a sine of 2 over x. And then we're going to have our integration coefficient. Let's see. All right. And so that is what this antiderivative or that indefinite integral that's given would equal. All right. What I want you guys to do is I want you to try part C. And I also want you to try part D. All right. If you get those correct, I'm going to give you bonus on your next quiz. Bonus on your next quiz. So get part C and part D correct. I'm going to give you a bonus on your next quiz, which is probably going to be on Thursday. All right. But I'll talk more about that on Wednesday when we get back to class. This is it with the video. Have a good day. Bye-bye.